Space weather can disrupt satellite communications, interfere with our TV signals, and disorient GPS systems. Now, we've known about these flowing streams of electricity in our upper atmosphere for years, but we've never had a way of tracking them until now. Jimmy Rhodes has the story.
The countdown to launch, a scene so familiar it's practically a cliche. So why would this group of University of Michigan students care? Turns out they designed and built one of the satellites that's on that rocket. So how did the launch go?
3, 2.
Well, they had to wait, and so should you, because a whole lot of work went into that moment. To get a sense of what was involved, I caught up with Assistant Professor of Aerospace Engineering, James Cutler.
What was the need, and who identified it?
The need was identified by the National Science Foundation, the NSF. And one of their big charters is space weather.
What does RAX stand for? What's RAX?
RAX is the affectionate name for the Radio Aurora Explorer. There'll be a ground radar that will transmit 2 megawatts into the upper regions of the atmosphere. RAX will fly above that region and pick up the radar echoes. And as RAX picks up those radar echoes, we will be able to image and see space weather plasma clouds.
Aaron Ridley studies space weather.
So what happens is that the particles from the sun get trapped in our magnetic field and they come down into our atmosphere. And those particles end up depositing a huge amount of energy, gigawatts of energy into our atmosphere. And so we're learning about space weather through the use of RAX.
And space weather is predominantly, at this point, I seem to be understanding energy.
Yes.
As you take a look at GPS signals and the integration of GPS into our cars, into our timing systems, in the cashiers when we make credit card transactions, airplanes, navigation, GPS is affected by space weather as well. There have been examples of power grids going out because of solar storms.
Scientists recognize the need for having a platform with a standard set of constraints that can hold unique payloads and that can be launched inexpensively. The standard platform is called a CubeSat. Cube is for the shape, and SAT is short for satellite.
This is an example of a CubeSat. It's a 10-centimeter cube, more or less, weighs about 1 kilogram, and it's an outside form factor with some definitions of how we interface to the rocket and things like that, but it's extremely simple. 10 centimeter by 10 centimeter by 10 centimeter, about 1 kilogram, and you get to figure out what goes inside.
According to electrical engineering student Alex Sloboda, the team packed a whole lot into those 3 CubeSat units.
Everything's basically built on a circuit board, and every circuit board does a certain function. And then we stack them all on top of each other, and they're all connected through several metal pins here that run along one side of the spacecraft.
Each layer in the racks had a team leader who oversaw the design and execution of the subsystem it housed. Second-year graduate student John Springman was in charge of the Attitude Determination Board.
What are these and how do they work?
Sure, these are magnets, and Earth has a magnetic field. That's how basic compasses work. So when you're out in the woods, your needle points north. It's actually aligning itself with Earth's magnetic field. So these do the same thing. They align our satellite with Earth's magnetic field.
To calibrate his system, John needed to be able to change the direction of magnetic fields, which you can do if you're willing to string up 12 miles of electrical wire in what's known as a Helmholtz cage.
So in the middle of the cage, that's a compass. And I'm going to change the direction of the magnetic field in the cage. And if you watch the compass needle, it's going to change direction.
Sure enough.
So that's just a demo for you that it's actually working. Now we obviously, when we're testing real hardware, we don't use a compass. We have electronic components that measure the direction of the magnetic field.
And this allows you to calibrate your devices.
That's right.
PhD student Sarah Spangalo was in charge of the position and time subsystem.
So we want to know the timestamp up to a millisecond in accuracy.
That accurate?
That accurate.
Oh my gosh,
Yeah.
there's no room for error.
Exactly.
Because we're talking about space weather.
Exactly.
If you don't know where you are in relationship to an anomaly,
Exactly. You're lost.
your data is meaningless.
Yeah. Similarly, our position requirements tell us that we need to know where we are up to about 1 kilometer. But we found that actually with our receiver and some of our simulation, we might be able to achieve 17-meter accuracy, which is phenomenal. This is the GPS receiver, and it connects to an antenna, which will be housed on the outside of the CubeSat, such that it is exposed to the GPS constellation at all times.
Alex also made a board, a part that didn't exist until he created it.
So somebody sends you one of these.
Well, not quite. The first step is I identified my requirements and found out what it needed to do. Then I designed this entire board in the computer. Then I ordered all the parts to go on it. And when it came in, I assembled it by soldering the parts on and then applying glue as needed. Then I programmed this computer right there. That's a little microprocessor, and that's basically the brain of this entire board. And so I wrote all the code for that, and now it does what it's supposed to do.
So, now that you know what went into that moment, about that launch.
1. Ignition. We have liftoff of the S-26.
So you're at the launch, there's a countdown going on. What's going through your mind?
It's absolutely unbelievable to think that, you know, the little receiver that I have my thumbprints all over is like actually inside racks, which, you know, we've spent hours and hours in the lab seeing and talking and thinking about and just shooting up into space.
I'll admit I was slightly nervous. You know, rockets don't work 100% of the time.
Excellent. I accept control of racks from your authority.
The next big hurdle was successfully getting data downloads from racks during its flyovers.
There we go.
It's coming in.
I don't know whether I witnessed success or failure there. What was that?
That was just a raw file downlink, and the file has been downlinked successfully.
When is this finally just pop the champagne success? When does that happen?
I think our biggest yes, we did it was probably when we got the first beacons, because that tells us that the core of the spacecraft is alive and working.
So, just as that launch wasn't the end for racks, racks is only the beginning for the students who made it happen.
What is this going to mean for these students?
They have flown something in space, they've designed it from scratch, and they will be catalysts and transformers in the aerospace world.